Alright, now let's go through some classical quantum algorithms. So as mentioned before, so how does quantum algorithms provide more powers? The intuition is that we can do parallel computations similar to the case of MP. So we've mentioned before, like if you have equal superposition state, you can create this using the Hardeman gate. So let's say you have 2 qubits. And if you perform, let's say, some kind of unitary transformation that encodes a certain function f, what you have effectively does is to perform f on all possible inputs. Calculate f on all possible inputs, i.e. You actually have done calculation for 0, 0, 1, 0, 0, 1, and 1, 1. But notice that you can only retrieve the results via measurement, and this is not very straightforward. So it's powerful, but not as powerful as you think. You might think. Yeah, let's go through our first algorithm, the Grover search. So what does this do? So basically, this is as the name suggests, this is a search algorithm. So specifically, it can solve set with quadratic speed up compared to a classical computer. So given a set formula, Grover search can find a satisfying assignment in poly 2 to the power of n over 2 compared to poly n times 2 to the power of n times needed on the classical computers. Okay, let's go through like how this works. So formally, we are given a polynomial time computable Boolean function which encodes the set formula. So this is a function that maps from an MB string to a binary output. So a satisfying assignment is a bit string where fa equals to 1, right? So we need to find this a. So we're assuming that there is a unique satisfying assignment. So effectively, what Grover's algorithm does is that it's trying out all possible x at each step and moving the state vector slightly towards end via some reflection. Okay, let's see how this works. So let's set up our calculation here. So we'll be using n plus 1 plus n qubits, where the first n bit is for the input. We'll need 1 auxiliary bit for computing the first reflection. And as before, we'll need to have some scratch space. The scratch space are needed for this bitwise observation to be unitary, i.e. reversible. So you'll be writing into this scratch memory. And so for simplicity, we'll ignore the scratch memory in all our algorithms, to simplify the notation. So a state like this will just remove the last n bit because they'll be used for scratch, and we'll just write the first n plus 1 bit here. Yeah. So now let's define two states, which is very important for these algorithms, and we'll be ignoring the normalizing constant here. You can easily derive them because this is just 1 divided by number of bases, and you take the square root. So the first state is the state U. This is the uniform superposition of all possible assignments. So we'll go through all possible assignments, and we'll add them up in equal superposition. We also define a second vector E, where this is the superposition of non-satisfying assignment. Yeah, so we'll go through all possible n-bit strings, but the one that we want, which is A. Yeah. So you add up x not equals to A, and that gives you E. Yeah, also define a shorthand for projection. So if you have a state W and you project to some state X, we'll just write this projected coefficient as Wx. And also we'll go through like what do we mean by reflection. Right, so if you can decompose some state vector into two orthogonal, it's a linear combination of two orthogonal state vector. So orthogonal is like, basically means non-overlapping. And yeah, you can decompose them into this. So actually, using this notation, I should be writing like WV1, but yeah, you get the point. So basically, you have pictorially you have V1 and V2. Yeah, so and W is something like this. So if you just yeah, and this length here is beta and alpha here. So by reflection around V1, or this computation we can easily done by just times and minus to the amplitude of beta. So pictorially, this is effectively doing this. Yeah, going from W to this W prime, where you times a minus in the amplitude of V2. Okay, so let's now define the first subroutine, which is the reflection around the state E. So remember that the E is the equal superposition of non-satisfying assignment. Yeah, so suppose we have we're now in a state W, so we can write it as such, where you have you go through all different possible bit strings, and each one has a different amplitude, and then you also have the auxiliary qubit, which is set to 0 at the start of this subroutine. So, so as shown before, we can convert any classical circuits into a quantum circuit. So let's first convert the stat circuit into an equivalent quantum circuit. We know we can do that, so this is just fx. So since f is computable in polynomial time, there are only so this quantum circuit will also only have polynomial number of gates. So yeah. So we'll be appending a C0 and RZ gate at the end, and we say and we will show that this is actually equivalent to doing a reflection around E. So let's go through this step by step. So here is our input state W. Yeah, so this is just W. We'll first do we'll first compute the stat formula using a quantum circuit. So we'll get fx here, fx here, and then we'll use the C0 gate to add it to the auxiliary bit. And notice that we can decompose this sum into two. Yeah, so this is effectively what we mean by trying all inputs. So that's what's happening here. If you have a superposition over all the possible inputs, then performing this step is equivalent to trying all inputs. So you can decompose this sum into two parts. The first part is the non-satisfying, so this is non-satisfying, and this is satisfying assignment, which is the A. So notice that For the non-satisfying case, we have fx equals to 0, so this auxiliary bit will be 0. And for this case, we'll have fx equals to 1, and yeah, so we'll have basically a1 is the state. So now let's do the RZ gate, which is effectively just doing so RZ gate will basically do this. Let's see. You would so this is a controlled rotation. So if the first bit, if the auxiliary bit is 1, we would do 180 degrees in the phase. So which is basically, times -1. This is equal to 2 pi I. Yeah. So we'll be doing a phase shift on the auxiliary bit, and effectively what that does is to change the sign of the second term into a minus. And as we have gone through before, this is exactly a rotation, a reflection around the first vector here. And note that the first vector, this one is effectively E. I mean, if we assume that all the Wx are equal superposition. Yeah, so after this we will do an extra step, right? So we'll do an extra step to remove this one. And we need to do that too, because all these subroutines assume that the auxiliary bit is already set to 0. So after the reflection, we need to perform this extra step. Yeah. So given this, so working with this state here, we basically can just do the first step again. Computing the set circuit F and apply it to the auxiliary bit using C0. So this will effectively remove this bit, because in this case fx is equal to 1. So in the end we will have the auxiliary bit equals to 0 in both cases. Yeah. So this is the reflection around E. Now let's talk about the second subroutine, which is the reflection around U. And after this, we will show how to combine these two steps together to do the Grover search. Now, suppose as before, we're working with the superposition states W in this, where the auxiliary bit is already cleared. So first note that Hadamard gates actually maps the uniform superposition state to the 0 state. I mean, this state is basically all zeros. Yeah. And if you apply this again, so if you apply Hadamard again to 0, you'll get back the uniform superposition. So as illustration, let's go through the 1 qubit case. So this is the uniform superposition. If you do the Hadamard, you'll find that you will end up in 0. And similarly, if you are already in 0 and you apply Hadamard gate, you will get back the uniform superposition. Yeah, and this is the same for if you do this for all the bits, you'll get a multi-bit Hadamard. That's effectively mapping between the U state and the all 0 state. Yeah. So how is this useful? So we can use this to implement the reflection around U. Because to do reflection around U is kind of troublesome. We can first, so effectively, let's say we have this reflection operator which can consist of multiple gates. What we can first do is to do a hard amount. So this will basically map. This is like change of basis. So yeah. So basically, it's changing U to mapping U to 0. So then you can reflect around 0. Yeah, so let me write it in this way. So if you want to do reflection around U, what you can do is to first do a head mount, then reflection around 0, and then do a hard mount again. So effectively conjugating. So basically, these two are conjugate. Reflection around U and reflection around 0. And since reflection around 0 is easier to implement, so we choose to do RU in this way. Alright, so let's first do the Hadamard operation. So this is the first step. So we'll do the Hadamard operation on our input state. So here is our input state. So after doing Hadamard, we will have all 0 bits. The all 0 state and all the other states. So this coefficient, I'm just going to call it alpha x, and here I'm going to call it w projected by w and u. Yeah. So the first coefficient will be exactly given by this inner product, and the second one I'm just going to write it as ax. Okay. So right now we're already have done the first step. The second step is to do the reflection around 0. Okay, to do that, we'll do a very similar operation as before. So previously we were doing this f. So f x equals to 1 only if x is equal to a. Right, so we'll copy this structure here. So we'll create a new function g where gx is equal to 0 only if x is equal to gx is equal to 1 only if x is equal to 0. Yeah, so we're effectively copying this structure here, but we just change the parameter from a to 0. Okay. And yeah, we'll do G then C naught as before. So what this does is that for all the other non-zero states, this G will output 0 here, and you will only output 1 for the 0 vector. Yeah. And then we can do the RZ gate again. But this time we will apply it to yeah. So we'll apply it to the auxiliary bit again. So notice that the auxiliary bit is 1 here, so we'll be rotating it 180 degrees. So we have a minus sign here. Yeah. And then we can again do the same thing, clearing the auxiliary bit by applying G and C naught again. So notice that the auxiliary bit for the first part is cleared. And then we can do the second Hadamard, which I'm not writing here. But basically, this procedure performs H R0 and H, and which is equivalent to do reflection around U. Okay, so right now we have these two operations at hand. We can start to assemble the Grover search algorithms. So first note that these two states are orthogonal because E is, all the non-satisfying assignments, so you would not have any overlap with A, so because this one will be basically 0, all the term will be 0. So yeah, so then you can see that we can write out E and A as orthogonal vectors here. And the angle between U and E will be very small, basically 1/2 and divided by 2, because they only differ by 1. The A vector. So basically, if you write out this one, you'll find that this is exactly like anyway, so this one will be a very small angle, which is the 1/2 to the power of m divided by 2. So each time we'll be doing two reflection, which we have constructed the gates for. So the first, so suppose we're starting with vector w. So first, suppose that the angle between w and u is alpha. Right. So this alpha is less than 90 degree. Yeah. And we'll call this angle between u and e theta. So theta is proportional to this to the power of -n/2, because so theta is actually just the arc cosine of 2 to the -n/2, which is a small angle. So when you first do this reflection around E, you'll get this double prime, which is on this side, and its angle with E is a plus theta. And then you do a second reflection. Right? You do a second reflection, and this time you actually get closer to A. Why? Because so suppose you're starting with the double prime, and doing reflection around U, you will get double prime prime, and if you calculate, because this angle is alpha plus 2 theta, which means the new vector will have also angle between double prime prime and U will be alpha plus 2 theta. Yeah. So going from alpha to alpha plus 2 theta. So each time you will be closer to the satisfying assignment state by 2 theta. Yeah. So after each two reflections, we'll get closer and closer to the correct state. So suppose we initialize W to U, then we can easily see that the number of times we need to get exactly to A is in the order of 1/theta, which is around 2 to the power of m/2 times, and that completes the proof. Because each reflection can be done in polynomial time, and you do it this many times, and then you get poly and 2 and 2. Yeah, so that's the kind of time complexity. So why is each reflection can be done in poly time? Because you can see that we can count the number of gates here. There are finitely many, and and also the only the only one that's slightly complicated is this F. So but this F, since it can be, we already assume that it's computable in polynomial time. So the equivalent quantum circuit only has a polynomial number of gates. yeah, so in the end, the reflection around E plus reflection around U can be done in polynomial time. Yeah, so that completes the proof for Grover search. So let's go into Simon's algorithms. Simon's algorithms finds a period of polynomial size circuits. So what do we mean by period? So this is exactly the cycles of the function. So like fx equals to fy, so you can, yeah, it's something like this. So fx is equal to fx plus bitwise, so XOR with an string a, and this will be equivalent. So yeah, so then we'll call a the period. So it's yeah, so the Simon's algorithm is interesting is because compared to the previous one, the Grover search, where it provides quadratic speedup, for this problem, the best classical algorithm takes exponential time, whereas the Simon's algorithm only takes polynomial time. Yeah, so it's a dramatic speedup compared to the classical case. Okay, let's see how it is done. So let's set up the qubits here. So in this case, we'll be using 2m plus m here, where m is used for scratch, and as before, we'll just not write it out. So we'll be using the 2n qubits here. So again, we'll first, apply the Hadamard to the first n qubit, and we get the uniform superposition in the first n qubit. And then we'll do the parallel step, where we, again, very similar. We have the quantum circuit for f, and then we run that on the first n qubit. So this is effectively searching over all possible inputs. Then we add it to the second n qubit, because we have assumed that this is like a n qubit to n qubit operation. Okay. Sorry, n bit to n bit operation. So notice that you can now decompose the first n qubit into this state, because we have assumed that this A exists, this period exists. So the first n qubit will effectively be a superposition between x and and the next period, basically, because if A equals to fx here. Yeah, so right now we will measure the second n bit, right? So basically measure the fx part, and so this will collapse the wave function to one particular input, right? So we fix this part, which effectively fix the corresponding x here, the inputs here. But notice that although we have done this computation, we cannot just extract A here, because each time when we perform the measurement on the first n bit, we will either get this one or this one. So at least from a single measurement, we will not be able to deduce the value of A here. So what we're going to do is that we're going to apply again the Hadamard operation to the first n bit, where I think I've mentioned this equation before. Basically, if you have so if you have some qubit x, and you perform the Hadamard operation. So n qubit, and you perform the n qubit Hadamard. So you'll be getting this state. So where y is all the possible n-bit strings, and this operation here is equivalent to xi, yi. So you do the dot product and mod 2. Yeah. So we use this equation here, so then we'll get this value. And notice that this value, yeah, we will only get y. So y is so we will only get non-zero coefficient for y if y satisfies this relation. Right. So okay, let's think about this slowly. So so basically a inner product y mod 2 will be either 0 or 1. If it's 1, then this term will be 0, then the whole term vanish. So if it's 0, then this term is 1, and you'll get this term, which is non-zero, which could be non-zero, which is correct. So the only way, so that means if you are able to sample a certain y by measuring the first n qubit, that means this y must satisfy, this relationship. Otherwise, you will have zero amplitude and you will never able to sample it. And notice that this is a linear equation. So if you get enough independent linear independent equation of this type, you can solve for A, because each time you measure, you'll get the value of y, right? So yeah, so basically you'll get you treat A as unknown. Then you can write n-1 linear equation. Yeah, you treat A as unknown. You have n-1 linear independent equations, and you can get A by solving for null space with SVD. Yeah, so that's how Simon's algorithms work. And notice that you are only doing this around linear times, linear times to the input side. And each time you are doing, again, this f takes polynomial times, and you apply some aggregate. So in total, each time for each computation, it takes polynomial number of times. So you have k times poly n, which is just still poly n. So the whole operation can be done in poly n times, and yeah, so that's a very dramatic speed up compared to the classical version. Okay, so now let's cover the one last quantum algorithm, which is the quantum Fourier transform. So this is the precursor that leads into Shor's algorithms, but due to time constraint, we're not going to Shor's algorithms. But with all this, with the quantum Fourier transform, you are almost there. Okay, so let's first revisit the discrete Fourier transform. So this is the classical discrete Fourier transform on Cn. Sorry, this should be n. So this is the usual definition, and you can simplify this part by just writing the nth root of unity. So this one equals to omega n, and then you get this term. And it's well known that if you do FFT, it takes n log n operations. Right? Now, so we can define so-called quantum Fourier transform, which is effectively doing the same thing, but you are using the amplitude, the probability amplitude of your Kribbe strings to store each individual term, this xk here, sk hat here. And to store, so because you have, for n qubits, you have 2n, so the number of qubits you need for this is only log n. And we will show that to do this operation, it only takes log n squared number of gates. Yes. So compared to the n log n here. So if we assume that each gate can be computed very fast, or similar to one operation in the FFT case, then this is more efficient algorithms. Yeah. And let's do some simplification here for the later on we will use this to verify that our circuit is indeed correct. So the QFT can be viewed as log n qubits unitary operation, so basically an n by n matrix where each entry is of this form. You can verify that this is indeed correct. And for each single basis state, so notice here, like when we are writing our state, these states are over all possible n-bit n qubit strings, right? So this n can be like 0, 1, 0, 0, 1, 1, something like that. So you can expand the basis string, I mean this n and k into you expand the binary the binary string into actual numbers. So for example, you can have, let's say 0, 1, 0. So basically this is 0 times 2, 0 plus 1 times 2 to the power of 1 plus 0 times 2, 2. So yeah, so basically this xi is the binary expansion of n, and this yj are binary expansion of k. And so if you do this QFT operation, if you look at the output, each of the basis k will have some amplitude, but let's say we just look at one of the k. Right? So you'll be mapping this state into, so yeah, effectively you're basically expanding this term here. Instead of writing kn, we expand it using this binary expansion, and we can write the exponent as such. So if each nk term has this structure, then we can be convinced that our operation is correct. Yeah. So now let's go over the QFT circuit. So this is one particular way to do QFT, where the circuit diagram is written out as such. So for each, so for the first qubit, you will first do a Hadamard and then the control phase gate, where the control bit is denoted here. Yeah, so Rj is defined as such. So the J defines the rotation angles. So it's the 1/2 to the power of J. So in this case, R2 is rotating 90 degrees. Yeah, so R3 will be rotating 45 degrees and so on and so forth. Yeah, so basically for the first one, you will do there are n gates, here, and for the second qubit there will be n-1 gates, and so on and so forth. So for the last one, there will be 2 gates and 1 gate, and overall this is n squared number of gates, which is log n squared. Yeah, but we need to verify that this is actually correct. Yeah, so let's do this now. So first of all, like for each bit, so let's say the first bit, you'll be mapped into this superposition between 0 and 1, equal superposition between 0 and 1, but where the 1 bit will have a phase shift of this term. And we can verify that, the control phase gate is indeed creating this phase shift. We can just verify this equation here. It all adds up. And here this thing in the square bracket here is the fractional binary representation. So yeah, so the first bit would correspond to 0.5 xi plus x1 times 0.5 plus x2 times 0.25 and so on and so forth. Yeah. So in the end, you apply a final permutation such that you swap the bit order into reverse. Okay. And so right now let's check the final this map. We'll use this previous equation here to check that this is indeed correct. So first write out for the case input bit where you will maps to. So you will map to this equal superposition with this phase here. Now for a particular output string where you can expand it into binary expansion here, we're writing in reverse. We'll reverse it first because after all these gates we'll apply a final permutation. So we'll reverse the order, and then we will check that we can calculate the phase factor for this particular y by this equation here. Yeah, basically what it does is that if y is 1 here, yk is 1 here, we will be multiplying this bit, this part. Yeah. So which is exactly this, because yk is 1. If yk is 0, then this whole term will be just 1, which corresponds to this case here. And so if we move the product to the exponent, we'll get a summation here. And if you rearrange the term, here, you'll find that this is exactly this form, which means that this operation is correct. And yeah, so that's how quantum Fourier transform works.